Welcome. I will comment on our paper Chiral Symmetry Conservation Principle. Firstly, my name is Alejandro Lopes Castillo. I was born in Brazil. My family is from Spain. I have an undergraduate degree in chemistry and in-house in physics and a PhD in theoretical chemistry, with postdocs in applied mathematics, dynamical system, and theoretical chemistry. I'm an associate professor at the chemistry department of the Federal University of São Carlos in São Paulo State. Some years ago, I initiated studies with a stochastic method using the Ehrenfest urn to treat and teach chemical kinetics as an alternative to differential equations. A few years ago, we investigated some chiral symmetry breaking problems using differential equations with randomness and stochastic methods. Our main objective was to understand the spontaneous chiral symmetry breaking driven by fluctuations in the absence of an enantiomeric excess. We consider some simple reaction mechanism, the Frank model, constituted by two autocatalytic reactions of two enantiomers and a competition reaction between them. In that sense, we studied the importance of the fluctuation and the chiral symmetry breaking in obtaining a final homochiral state. We use deterministic and stochastic methods to describe these processes. The stochastic methods contain fluctuations, but deterministic ones do not. We can summarize the following results for both methods. Deterministic methods strictly favor the final homochiral states, which initially has an enantiomeric excess. However, this last result is perhaps incorrect or incomplete, since the initial enantiomeric excess must be considered quantitatively if the statistical fluctuations is present as in nature, and the strictly terms must be substituted by probabilistically. The stochastic method can better describe chiral symmetry break and consider the following probabilistic law. Stochastic methods probabilistically but not strictly favor the final homochiral states with initial enantiomeric excess. This implies that a final homochiral results can be different from that with an enantiomeric excess. This is important since a chemical reaction mediated by a chiral catalyst can result in a final product with different chirality, mainly if the catalyst is poorly chiral. This could be extremely important in drug synthesis. This probabilistic law we obtain may contain the seeds of the chiral symmetry conservation principle. This law implies that if a system is globally racemic, it will remain racemic even after numerous local chiral symmetry breaks. For example, a racemic system could be broken in two sets of subsystems with the same chirality, but quantitatively different. We can assume that one of the sets has more subsystem than other due to the breaking process considered. The final global system will remain racemic if we consider the statistical law quantitatively applied to each subsystem. However, the same results will not obtain in the deterministic analysis, since the final chirality will be the same of that of the sets with more subsystems. There are many experiments in which spontaneous chiral symmetry breaking was observed. A classical experiment is a Condeput's work on chiral sodium chlorate crystal obtained by evaporation of racemic solutions. A series of experiments are carried out, and in the end the crystal with one type of chirality, homochiral states, are obtained for half of the experiments and another type of the other half. Consider a single experiment, the breaking of chiral symmetry in space is observed. However, a global symmetry breaking is not effectively observed for a temporal average of many experiments. That is, the sum of all crystal obtained in our experiment would represent a racemic system. Based on this and other experiments and the probabilistic law, we can formulate some question. Is the chiral symmetry conserved in the space-time? Is there a chiral symmetry conservation principle? Is the conservation statistical or deterministic for a microscopic system? How does the chiral symmetry transfer? Or conversely, was there a primordial global chiral symmetry breaking? Or more specifically, is our universe chiral or only locally chiral but globally non-chiral? What is the consequence of a chiral symmetry conservation principle for our universe? Can this imply in one or more chiral universe? If one wants to avoid multi-universe, like in quantum mechanics due to measurements process, it's necessary to understand the problems consider only one universe. What is the consequence of these constraints? We tried to answer these questions and others in our paper Chiral Symmetry Conservation Principle, published last year in Chirality Journal. Thank you for your attention.